Hello everyone. It's my honor to participate in this conference. My topic is a story about VirtualBox escape. First, introduce myself. I'm a security researcher of Chen Security Research Lab. In the past years, my work involved bug hunting and exploiting technique, mainly in virtualization, IoT, and the OS kernel. Chen is an excellent network security company in China. Our real-world CTF has received international attention and recognition. We also welcome everyone to attend it. The agenda for this talk. First, we will introduce the architecture of VirtualBox and its attack surfaces. Then, introduce the bug hunting ideas for these attack surfaces, including code review and fuzz methods. Next, we will explain the course of some vulnerabilities through the real cases. Finally, we explain the process of exploiting the vulnerabilities and show the final effect. Part 1. VirtualBox Overview. Let's look at the architecture of VirtualBox. Okay, let's see the picture shows. This is a very common virtual machine architecture. And other virtualization systems such as VMware and HITB also have similar architecture. That is divided into two parts, host and guest. The host usually refers to the main operating system that running the main virtual machine program. And the guest usually refers to the operating system that running in the virtual machine. The main security design of a virtual machine is system isolation. So its main threat model is to attack the host through the guest. As a bug hunter, we need to observe the architecture from the perspective of an attacker. This means that we need to understand how the guest communicates with the host. Next, we will introduce in detail how they communicate. First, let's learn about general communication. As the name implies, general communication is a common communication mode in all virtualization systems, which emulates the communication of real computer devices. This communication method can make the guest run without protection, because there is no need to install additional communication components in the guest. As shown in the figure in the VirtualBox, the guest runs the communication instructions through the system's own device drivers, and the host's hypervisor will capture the instructions and pass the message to the corresponding emulated device component. The emulated device will parse the message from the guest and implement the response operation. General communication contains three types of methods. They are I/O method, MMIO or DMA method, and other special methods. The method instructions is related to the architecture of the CPU. For example, in x86 there are in, out, move instructions and so on. The I/O instructions communicate with the devices through the I/O port. The move instruction communicates with the devices by reading and writing special guest physical addresses. For other special instructions, messages are passed through special registers. since the processing of special instructions doesn't include the pairs of complex state, it just emulates the behavior of the CPU. So we don't care about it for this time. In the VirtualBox, we mainly care about I/O, MMIO, and DMA method. Obviously, these instructions need to be run in ring 0 of the guest. So when we test a virtualization platform, we usually need to load a custom driver in the guest to do it. In a virtualization system, there is a type of device called emulated device. Because the device emulates the real hardware device, since the real devices usually use general communication with system software. So in a virtualization system, general emulation is usually implemented by emulated devices. In the VirtualBox, there are many emulated devices which provide a large attack surface. As shown in the figure, motherboard chips, graphics cards, network cards, sound cards, and storage controller, and so on. These are all emulated devices. Each of these devices will emulate a special model of hardware. For example, the network card emulates E1 key. USB emulates OHCI controller. And storage emulates AHCI controller. So we can refer to the datasheet of the real device to understand the principle of its implementation. This is a good way to learn about emulated devices. Next, let's talk about special communicates. In addition to general communication, virtualization systems usually include special communication methods. As shown in the figure, because the operating system itself can't recognize the special communication protocol, the guest needs to install additional drivers provided by virtualization systems. The VirtualBox contains many such drivers, such as the VBox guest, VBox service, VBox video, and so on. The implementation of these drivers depends on the guest operating system. The drivers will communicate with the corresponding device in the host. I will explain what devices are there later. The essence of special communication and general communication is the same. They all communicate through I/O or MMIO instructions. The main difference is that the special communication protocol is privatized, and it doesn't exist on any real hardware. The purpose of this is to make it easier for developers to make the features of virtualization, to make communication more efficient. For example, the network card is a key component that affects the system performance. Through special communication, developers can make an efficient ring buffer for guest and host communication. In addition, special communication is also used to realize the unique functions of the virtual machine, such as folder sharing and file dragging, and so on. In VirtualBox, the host implements these functions as devices. Finally, there is a very interesting place to use special communication, which is BIOS. The virtualization system may add custom I/O port or MMIO to the emulated device for the convenience of bears. Therefore, emulated devices are not necessarily all general communications. As shown in the picture, VirtualBox has many special devices, such as network card device VirtualIO Ethernet, graphics device SVGA 3D, storage device VirtualIO SCSI, and video acceleration device VHWA, and so on. There are also some devices that implement special functions, such as VirtualKD device for debugging, and Vmm devices that provide basic protocol, HGCM, for various special services, such as folder sharing, file dragging, and other services. Therefore, special communication also has a large attack surface, but due to its private nature, you need to read the source code and reverse the binary to know its details. Okay, next, let's talk about backend communication. In virtualization system, only the device is not enough. The device receives only the raw data, and further processing needs to be performed by the backend. For example, the network card device only receives the network data packets, and how to forward it needs to deal with the backend of the Ethernet or IP protocol stack. In addition, USB devices only accept USB data packets, and the specific functions of USB have to be done by the backend. There are also storage devices which just receive file data. Where to read from and write to, it also needs to the backend to decide. In the VirtualBox, there is usually a driver component that acts as a bridge between the device and the backend. The driver is not a kernel driver, but a design model in the code. Therefore, guest and the backend constitute indirect communication. We can think of it as a new attack surface. Next, we will introduce various backends one by one. The first is USB backend, and the picture shows the front device of USB is USB controller, such as OHCI, EHCI, and XHCI. These are standard USB hardware protocols. When the controller receives the USB data packet, it needs to be forwarded to the corresponding USB backend. There are many kinds of USB backends, such as storage USB, camera USB, and network USB, and so on. They will define a unified interface, and backends interact with the front device through URB. Therefore, the USB attack surface has ended URB and barrier backends. Next is the storage backend, and the picture shows the front device of storage is storage controller, such as AHCI, LCSI, and ATA. These are standard storage hardware protocols. When the controller receives the disk data packet, it needs to be forwarded to the corresponding storage backend. In the VirtualBox, the backend represents different types of images, because the format of each image is different, so different backends are needed to read and read. There are many kinds of storage backends, such as VMDK, VDI, RAW, and so on. Similar to USB, VirtualBox defines a unified interface for these backends. and the bridge driver is the VD components. Therefore, the storage attack surface has an VD component and various storage backends. Next is Vmm Device Backend. Vmm Device doesn't emulate hardware device. It is just a custom host and guest communication device. It provides a communication basis for sharing files, dragging files, and other functions. Therefore, as shown in the figure, its backends are various devices. These devices are specific to virtual machine. They need to install additional drivers in the guest. Similar to the previous backends, different devices has a unified interface that is HGCM. Therefore, the Vmm device attack surface had ended HGCM and various devices backends. Next is SVG 3D backend. SVG 3D is a 3D graphics device of VirtualBox. It emulates the function of GPU. It isn't an emulated hardware device. It customizes the data format, so additional drivers need to be installed in the guest. After the device receives the 3D data from the guest, it needs to be converted to a data format that can be recognized by the host 3D graphics library. Therefore, its backend is DirectX and OpenGL, which are used for Windows and Linux respectively. Since the graphics library is not much different, so the bridge driver components are not used here. Therefore, the SVG 3D device's attack surface has an DirectX and OpenGL backend. Next is network backend. The backend of network card device is mainly used to process the network packet protocol and then forward it. VirtualBox uses a third-party open source library, SLIRP. Since the library can be easily compiled and run independently, many people have used it. Similar to the previous backends, it also has a unified interface that is DRV-NAT. Therefore, the network device attack surface has added DRV-NAT and SLIRP backend. Okay, after understanding the communication methods and attack surfaces of VirtualBox, I will discuss how to bug hunting. The first method is code review, but it isn't only a review. I also need to consider how to fuzzing during the review process. Next, I will discuss the key points of reviewing VirtualBox. It also applies to other virtualization systems. Device is an important attack surface of virtualization system. First, let's look at the initialization process of device. In the VirtualBox, each device has a device registration structure object, which contains the basic information and callback functions of the device. These callback functions describe the entire life cycle of the device. As the picture shows, these are some callback functions including the PDM structure. For example, the initialization function of the device is pfunction constructor, and the startup function is pfunction power on, and the restart function is pfunction reset. These are unified device interface defined by VirtualBox, which is called by the VirtualBox main thread at an appropriate time. And shown in the figure, the picture on the right shows that the main thread adds all device registration objects to the device list. Here you can see which devices are registered in VirtualBox. And the picture on the left is the device registration structure of the E1K device, which is a good entrance to understand the E1K device. The most important callback function of the device is construct. It is a callback function in the device registration object structure, which is called by the PDM device init function. The constructor function is the initialization function of the device. Especially, it shows which attack surface the device has. As shown in the figure, this is the constructor command code logic. Among them, we need to focus on IO port create, IO create, and thread create. IO port create registers the IO port and IO callback for the device, so that we can use the in and out instruction to call from the guest. IO create is similar to IO create. It can be called by the move instruction in the guest. Thread create creates the working thread of the device, which contains the main logic of the device, so which requires us to review in detail. As shown in the figure, the device is registered with an IO port and a MMIO. We can easily find their callback functions. They are the parameters of the registration function. Next, let's talk about IO and MMIO callback functions. As mentioned earlier, there are some instructions that can trigger IO and MMIO callbacks, such as the in and out instructions and move instruction. As shown in the figure, their callback functions are similar, and we need to focus on is which parameters the guest can control, such as offsite parameter, usually to parameter, CB parameter. Let's take the out instruction as an example. The offsite parameter represents the offsite based on the IO port. The usually to parameter is the value written. The CB parameter represents the length of the usually to parameter. Reviewing the virtualization systems usually starts with the IO callback functions, because this is the gateway for communication between guest and host. As shown in the figure, this is a callback function for the out instruction. Usually a device contains various registers. We can see that when the offsite parameter is 0, usually to parameter represents the index of the registers where to be operated. When offsite parameter is 1, usually to parameter represents the value to be written to the register. This register is specified when the offsite parameter is 0. As shown in the figure, this is a MMIO callback function, triggered by the move instruction. It should be noted that the move instruction here is to write date to a fixed guest physical address. The physical address can't be direct accessed in the guest. You need to map the virtual memory first, and then move it. In addition to I/O port, there is another important communication method, directly memory access. In this way, the host and the guest communicate by directly reading and writing the physical memory of the guest. This is a very efficient communication mode, but it needs the host and the guest to negotiate the physical address. This process is usually completed by I/O port communication. For example, the guest sends a physical address to the host through I/O port. Then, the host reads more data through the physical address. In this way, the guest data will enter the host space. VirtualBox usually uses the two functions shown in the figure to complete the guest physical address reading and writing. We need to care about its three parameters: GC physicals, PV_buf, and CP_write. GC physicals is the guest physical address. PV_buf is the buffer to be written and read. CP_write or CP_read is the length of reading and writing. As shown in the figure, this is an example of reading guest physical memory. This is a function in the E1K network card device, which obtains data packets by directly reading the guest physical memory. Therefore, this is also an important attack surface we need to care about. Even more important than I/O, because the data read in this way will be larger and more complex. Next, we introduce the code review of backend communication. The first is USB backend. Similar to the device, the USB backend defines the PDM USB register structure, which unifies the interface for the USB backend. What we need to focus on is the pfunction URB quick callback function, and the USB packet sent by the guest is finally processed by this function. Another important structure is VHWA URB, which defines the bridge between USB controller device and the USB backend. As mentioned earlier, after the USB controller receives the USB data packet from the guest, it first sends it to the URB. URB marshals the data and then sends it to the USB backend for processing. Therefore, the URB marshalling process needs our attention. And we also need to focus on the AB data and the CB data field in the URB structure. The AB data field is the USB data buffer, and the CB data field is the length of the USB data buffer. They all are affected by the guest. As shown in the figure, this is USB backend registration function. From here, you can find all registered USB backends. As shown in the figure, this is a quick callback function of the USB MSD backend. The endpt field represents the type of USB data, and the USB packet is stored in PURB parameter. Almost every USB backend has such data processing logic. Next, we talk about storage backend. The storage backend defines the VD image backend structure, which unifies the interface for the storage backend. What we need to focus on is the pfunction read and pfunction write callback function, because the final read and write to the hard disk will be handled by them. As shown in the figure, the picture on the left shows all the storage backends in VirtualBox. They represent different disk image file formats. The picture on the right is the storage backend structure of VMDK. It contains various callback functions for this type of image. Next is the network backend. As mentioned earlier, the network backend uses the sleep open source library. A sleep input function is a state processing intro function. The buffer parameter contains the network date to be sent. CB buffer is the length of the date. When the network card device receives the network date packet, it will be sent here for the processing of the Ethernet or IP protocol stack. Next is Vmm Device Backend. The Vmm Device Backend defines the VBox HGCM service function table structure. It unifies the interface for the Vmm Device Backend. As shown in the figure, the structure contains many callback functions. They are responsible for the entire life cycle of HGCM communication. What we need to focus on is the pfunction callback function, because it is the main function of the service. VBox HGCM service load is a function used to initialize the service. Each service contains this function. We can find all services through this function. In this function, service is registered for the table object. As shown in the figure, this is the core function of the guest probe service, where E function, C parameters, and PAP parameters can be controlled by the guest. We should pay attention to them. Next is SVGA 3D backend. As mentioned earlier, SVGA 3D backend includes DirectX and OpenGL. As shown in the figure, they define a unified interface, so that the SVGA 3D device only needs to call the interface and doesn't need to define the backend. The interface of SVGA 3D backend usually corresponds to the SVGA 3D command. As shown in the figure, the guest sends a service-defined command, which will be processed by the Vmm SVGA 3D service-defined interface. We need to pay attention to P command parameter, which is date controlled by the guest. Okay, after introducing the code review, we do some interesting things. How to automate bug hunting. First, introduce a static detection method, CodeQL. CodeQL is an analysis engine used by developers to automate security checks, and by security researchers to perform variant analysis. CodeQL compares code to a relational database, which is queried using SymQL, a declarative, object-oriented query language designed for program analysis. All in all, CodeQL can be used to find code logic programmatically. The CodeQL basic workflow is that based on the analysis of historical vulnerabilities, we write queries to find code patterns that are semantically similar to them. CodeQL analysis consists of 3 steps: preparing the code by creating a CodeQL database. Second, running CodeQL queries against the database. Third, interpreting the query results. For example, as shown in the figure, this is create a CodeQL database of VirtualBox. For example, we now want to find out the length parameter of memory copy controllable by the guest. First, we determine the source of the date, and the picture shows Take URB as an example here. PURB contains a user controllable length, so find functions that use PURB. Second, we need to determine the destination. The destination here is the third length parameter of memcopy. So we look for the third parameter of memcopy, and the source of this parameter is related to PURB. Third, and date blue date by source date to query. For example, in exception A to B.C, the date follows from A to C. Finally, execute the query. We use date flow. It will search the path automatically. Next, we check the result and find vulnerabilities. The script has more than 30 results, of which more than 10 are duplicates. Finally, after a short inspection, 2 vulnerabilities are found. Okay, next, let's try to use dynamic fuzzing. Here I use the AFL++ tool. AFL is a fuzzer that employs genetic algorithms in order to efficiently increase code coverage of the test cases. AFL++ is a superior fork to Google's AFL. More speed, more and better mutations, more and better instrumentation, custom model support, and so on. For more details, please refer to GitHub. There are 3 steps to fuzzing source code. First, compare the target with a special compiler that prepares the target to be fuzzed efficiently. This step is called instrumenting a target. Second, prepare the fuzzing by selecting and optimizing the input corpus for the target. Third, perform the fuzzing of the target by randomly mutating input and assessing if the generated input was processed in a new path in the target binary. AFL++ has 4 modes. The advantages are shown in the figure. Please refer to GitHub for details. Using AFL++ in VirtualBox, I encountered 4 kinds of problems. The first is the problem of failing to compare. The second is the problem of choosing whether to fuzz as a whole or split into independent components for fuzzing. In addition, where is the loop of fuzzing? Finally, how to improve the performance of fuzzing. First, let's talk about compare problems. When comparing VirtualBox with AFL++, the first thing I thought of was to modify configure file to change the CC and CXX to AFL C-long first and AFL C-long first ++. But there were a lot of errors when comparing, and even C grammar that C-long couldn't recognize, so that I couldn't fix it easily. After research, I found that the source code that failed to compare is not related to the component we want to fuzz, such as UI-related, kernel-related, and some assembly files. Therefore, I consider mixed compilation. The source code of fuzz needs to be compared with AFL++, and the other are compared with original GCC. Fortunately, the compilation framework of VirtualBox is very easy to do this. KMK is a template-based compilation framework. VirtualBox defines a template for each module. we only need to modify the specified template. So we can do like this. Create an afl.kmk file in keybuild tools directory, which can be copied from keybuild tools gxx64.kmk file, and write the afl compilation tool into it. Next, modify the config.kmk file and change the compilation tool of the first model you need to AFL. Then you can compile it. There may still be some errors, but they can be easily resolved, so I won't repeat them here. The most common use of AFL is to fuzz a separate library, such as lib.xml. There are also some libraries that can be fuzzed in VirtualBox, such as slip, shaderlib. But this is only a small part of the VirtualBox. Most of the others are strongly coupled with the core, such as the devices and the backends. These components are difficult to separate and run independently. Therefore, split files will not be able to cover completely. In the end, I chose the fuzzer complete VirtualBox. Because VirtualBox is not a standard input and output program, and it isn't a one-time execution program, so we need to make it accept input and end after processing. Therefore, I designed a VirtualBox fuzz cycle. First, using VBox headlights and the startup program, it will avoid loading the UI program. Second, I add the pfunction files entry callback function to the Vmm Device register structure, which is a fuzz entry for each device. And after power up, I will call the pfunction fuzz entry function of each device. Finally, close the VirtualBox. The main fuzz code is in pfunction fuzz entry, and we can directly call the IO port handler and MMIO handler. Its parameters are taken from the input of AFL. In addition, for directly physical memory read operations, we also need to modify it to obtain from the AFL input. As shown in the figure, the picture on the left is the fuzz entry function of the HDA device, which mainly performs a fuzz test on the MMIO handler of the HDA device. And the picture on the right is the fuzz entry function of the PCNet device, which performs a fuzz test on the IO port handler of the PCNet device. As shown in the figure, this is the hook to the directly memory access function, and its state source is changed to AFL, which also makes a fuzz task. When we complete the first version of fuzz, it runs very slowly, about 2 times in a second, which couldn't meet our needs at all. So we started the optimization route. The biggest reason for the slowness is the startup process, so we use persistent mode, a core feature of AFL++. First, we load AFL loop after power up, and then after the fuzz entry is complete, manually call device reset to ensure the consistency of the state. But even this is very slow, because the reset of the device is a waste of time, and it can't be placed outside the loop. Therefore, we need to optimize the reset of each device. After optimization, it finally meets the requirement of fuzz. By using the above three methods, 10 plus vulnerabilities were finally found. Next, I will introduce some of them. Part 3. Case Study. First, let's talk about CVE 2021-2112. This is a memory corruption in USB MSD backend from guest to host. As shown in the figure, we can start from the OHCI controller device and cite OHCIED and OHCITD through I/O port. Then, toStructure contains the physical address of the data packet and the ID of the backend. Next, start OHCI block list. The controller will read the USB data from the previous physical address. Then OHCI sends the data to URB core. URB core marshals the data and calls the quick function of MSD by the backend ID, and sends the marshaled data to it. Finally, when parsing the USB data in the MSD quick function, the length was not checked, so resulting in OOW. Let's see the source code. As shown in the figure, CB copy can be controlled by the guest. Because the value is not checked, it leads to out-of-bounds writing. This is the stack trace at the crash. We can easily see that this is a vulnerability in the USB MSD backend, which caused the memory to write out of bounds. Next, let's talk about CVE 2021-2131. This is the stack trace at the crash. As shown in the figure, this is an OOW of URB core. It is caused by URB core's incorrect check of the data length. We are using EHCI controller here. Next, let's talk about CVE 2021-2120. This is the stack trace at the crash. As shown in the figure, this is an OOR of the LSI logic as CSI device. This is a device vulnerability. It can be seen from the stack trace and it is caused by the correct checking of the length field when processing the I/O port. Next, we will complete the last step, the exploit. Here is the CVE 2021-2119 as an example. First, let's talk about the cause of the vulnerability. The VBox SSI read string function is the rip-in instruction handler of the SSI device. CB transfer field is controllable by the guest, and the lack of checks on CB transfer and CB buffer left in VBox SSI reading string function leads to OOR. The more serious problem of this vulnerability is that the CB buffer left intake overflow caused by the vulnerability in VBox SSI read string, which can bypass that check of CB buffer left greater than 0 in VBox SSI writing string function. This will be resulting in OOW. Therefore, the vulnerability can cause out-of-bounds read and write, which is very suitable for exploitation. This vulnerability has been exploited by SauerCloud team in real-world CTF. The write-up link is as follows. Its version mainly uses HGCM-related objects. For more HGCM usage, please refer to SauerCloud's write-up. Today, we will introduce another exploit primitive, which is related to SVG3D. VirtualBox is very difficult to work on the root of 3D. The old version of VirtualBox 3D is Chromium framework. That brings many security vulnerabilities to VirtualBox. Therefore, this module was deleted after version 6.1, and the useful primitive CR connection and CR client was also deleted. Then, I analyzed SVGA 3D, which replaced the VBox 3D, and found that it also has a great use of primitives. The exploit primitive are mainly VM SVGA 3D mapmap level object. The mapmap object contains a data buffer point and a length field. The content of data buffer can be written and read by the guest. In addition, the mapmap object can also be allocated in any number, and it can also allocate for memory in combination, which means it can be adapted to many lengths. This is an excellent spread object. When we use vulnerabilities to change its data buffer point, we can cause arbitrary address reading and writing. The SVGA 3D command to apply for this object is SVGA 3D command service define, and the SVGA 3D command to read and write data is SVGA 3D command service DMA. The next thing becomes very easy. Through the heap spray, we can get the heap as shown in the figure. Get a series of mapmap arrays, and then free some of them, create some holes. Next, we create a vulnerable SCSI buffer object assigned to the previously released address. Then at this point, the heap is laid out finished. Next, modify the data pointer of mapmap by reading and writing out of bounds, resulting in arbitrary address reading and writing. With arbitrary address read and write primitives, you can easily find some arbitrary change RIP methods, such as modify some virtual table points, and there are many ways to leak the base address information, such as the layout of SVGA 3D context objects, which will not be described in detail here. Part 4. Demo time. Let's see the effect of the final escape. Thanks very much for the help of my colleagues. They are Kelvin, M4X, Swing, Exploit, F1YY, Leo IMXG. Thank you very much for watching. If you have any questions, please contact me email directly.